Welcome to this presentation on finding the kth smallest element in a binary search tree. In this session, we will walk through the problem, provide examples, explain the approach, and discuss the solution in details. Let's begin. Our goal is to find the kth smallest element in a binary search tree, BST. A BST is a tree where the left subtree contains values smaller than the root and the right subtree contains values greater than the root. We are given an integer k and a BST. We need to return the kth smallest element. If k exceeds the number of elements in the tree, we return -1. Let's look at an example. Given the BST 2, 1, 3 and k equals 2, the second smallest element is 2. We can see that the tree is already sorted in ascending order and 2 is the second value in this sorted list. Next, consider the BST 2, 1, 3 again, but this time k equals 5. Since the tree only has 3 nodes, the fifth smallest element does not exist. Therefore, the answer is -1. Here we have another example. For the BST 20, 8, 22, 4, 12, n, 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 10, 14, and k equals 3, the third smallest element is 10. If we perform an in-order traversal of this tree, we get the sorted list 4, 8, 10, 12, 14, 20, 22. The third smallest element is 10. To solve this problem, we can use in-order traversal of the BST. In-order traversal processes the nodes of a BST in sorted order, left subtree, root, and then right subtree. By performing an in-order traversal, we can directly access the kth smallest element. Let's outline the steps involved in the algorithm. First, we initialize a stack to assist with the in-order traversal. Then we traverse the tree by pushing nodes to the stack until we reach the leftmost node. After that, we pop nodes from the stack and increment a counter. If the counter equals k, we return the current node's data. If we reach the end of the traversal without finding the kth smallest element, we return -1. Here's the C++ code for the solution. We start by defining the kth smallest function, which accepts the root node of the BST and the integer k. We declare a stack to perform an iterative in-order traversal and a counter to track how many nodes we have visited. As we begin the traversal, we push the current node onto the stack and move to the left child until we reach the leftmost node. We keep pushing the nodes onto the stack as we go deeper into the tree. After reaching the leftmost node, we pop nodes from the stack. For each node we pop, we increment the counter. If the counter equals k, we return the node's value as the kth smallest element. If we complete the traversal and haven't found the kth element, we return -1. Now let's discuss the time and space complexity of this solution. The time complexity is big O of n, where n is the number of nodes in the BST, because in the worst case we might need to visit every node. The space complexity is big O of h, where h is the height of the tree, because that's the space used by the stack during traversal. Let's consider some edge cases. If k exceeds the number of nodes in the BST, we return -1. If the tree contains only one node and k equals 1, we return the root node's value. If k equals 1, we immediately return the smallest element, which is the leftmost node in the tree. In conclusion, we can efficiently solve the problem of finding the kth smallest element in a BST using in-order traversal. This approach ensures an optimal time complexity of big O of n and a space complexity of big O of h, making it well suited for large trees. Thank you for your attention.